children. So yesterday we have done a property of phenol, that is electrophilic substitution reaction in the case of phenol. Yesterday we have discussed 4 reactions. The 4 reactions we have discussed yesterday was number 1, halogenation, in which we took example of bromination. Number 2 we did was nitration. Number 3 that we did was sulfonation. Number 4 that we have discussed was nothing but your Friedel-Crafts reaction, in which explained to you that the yield of the reaction is very, very less, because phenol reacts with the catalyst and hydrous AlCl3. The output of the reaction is going to be very, very less. Today we are going to discuss 2 more electrophilic substitution reactions in the case of phenol. Today we are going to also make an important drug called aspirin, and then we will see some conversions, and that will be the end of this chapter. Today we are going to end up this chapter. We are doing chapter called phenol ether. So what we are discussing is now the 5th reaction. Again an electrophilic substitution reaction of phenol. It's a named reaction. The reaction is called Reimer Tiemann reaction. It's called Reimer Tiemann reaction. It's a reaction in which we can convert phenol into a compound called salicylic. In this named reaction, we can convert phenol into a compound called salicylic. You just see the IUPAC name of salicylic also. So it's a Reimer Tiemann reaction in which we will be able to convert phenol into salicylic. What we do in this reaction is we take phenol. We have to have a solution of phenol. We've already discussed phenol is sparingly soluble in water. So we are going to dissolve phenol in dilute NaOH. You already know why phenol dissolves in dilute NaOH, because phenol is acidic in nature. It will react with NaOH to form a water soluble salt. So phenol is dissolved in dilute NaOH. It converts into a salt called sodium phenoxide. You get the formation of sodium phenoxide. That's the first step. We are supposed to make the solution of phenol in dilute NaOH. We are not using water as a solvent because phenol is sparingly soluble in water because of the big non-polar hydrophobic benzene ring. This already we know. In the next step, we are going to react sodium phenoxide with chloroform. Temperature would be around 340 Kelvin. So next step, the solution of sodium phenoxide is treated with the chloroform under 340 Kelvin temperature, followed by acidification. You will get a compound called salicylic. This is what is called salicylic. You get an ortho product. This is commonly called as salicylic. Now would you mind giving its IUPAC name? Can you try its IUPAC name? There are 2 functional groups, one is OH and the one is CHO. Which one will be given preference? CHO. So we number it from here 1, 2. So its IUPAC name will be nothing but 2-hydroxy benzaldehyde. So the IUPAC name of salicylic is nothing but 2-hydroxy benzaldehyde. And again it's an example of an electrophilic substitution reaction. It has a mechanism also, but in the CVAC we will not be discussing its mechanism, but it is an electrophilic substitution reaction. If you want to know, I can tell you in this reaction the electrophile which is involved is as follows. This is the electrophile which is involved in this reaction. This electrophile is called dichlorocarbene. That is the electrophile which is going to attack on phenol in this case. This is called dichlorocarbene. Obviously that chloroform converts into dichlorocarbene, which reacts with phenol at ortho position, electrophilic substitution reaction. H plus will be replaced by this, followed by the other reaction, and ultimately you are going to get salicylic. We are not going to into the mechanism detail of this Reimer Tiemann reaction. Now the next reaction that we are supposed to discuss is called Schimdt reaction. Schimdt reaction. Again a named reaction. Schimdt reaction. Again, an example of electrophilic substitution reaction in which carbon dioxide acts as an electrophile. In this, we can convert phenol into an acid called salicylic acid. And salicylic acid is used to make an important drug called aspirin, the medicine called aspirin. What is the use of aspirin? It is used to relieve pain as well as it brings down the body temperature. So later on we are going to convert salicylic acid into an important drug called aspirin. So in Kolbe-Schimdt reaction, what we do, we convert phenol into salicylic acid. So again we start from phenol. We have to dissolve phenol, and even like if you want to make a solution, what solvent will be using? Dilute NaOH. Why phenol dissolves in dilute NaOH? Because of its acidic nature. It will react with dilute NaOH and will convert into its sodium salt. You will get the formation of sodium phenoxide. Through the solution of sodium phenoxide, we are going to pass carbon dioxide, which is an electrophile in this case. Temperature would be using 400 Kelvin. The pressure around 400 atmosphere, followed by acidification. The second step would involve acidification, and you get a compound called salicylic acid. And as I told you, this is again an electrophilic substitution reaction. The electrophile involved is carbon dioxide. Carbon dioxide is an electrophile attacking at the ortho position. This compound is called salicylic acid. Salicylic acid is used to make aspirin. But in Kolbe-Schimdt reaction, we are supposed to convert phenol into salicylic acid. Now, can you try its iopectine? Very simple. Out of these two groups, which has a higher preference? COH. So its iopectine would be 2-hydroxy-benzoic acid. Like it is 2-hydroxybenzaldehyde, this would be 2-hydroxy-benzoic acid. So we have discussed two more electrophilic substitution reaction of phenol, making the total tally to 6. Today we have discussed Reimer Tiemann reaction, in which we make a compound called salicylaldehyde, and Kolbe-Schimdt reaction, in which we get the formation of salicylic acid. I told you why salicylic acid is important, because it is used to make an important medicine called aspirin, which brings down the body temperature and also it relieves you from the pain. It's a pain reliever as well as it's used to bring down the body temperature when there is a fever. So now let's try to convert your salicylic acid into aspirin. Let's see the preparation of aspirin. So let's make aspirin. Aspirin can be made from salicylic acid by simply doing acetylation of salicylic acid. We take salicylic acid and subject to a process called acetylation. We are supposed to do its acetylation. We are going to get a drug called aspirin. Let's just see what is acetylation. So what we do? We take salicylic acid. We react it with a compound called acetic anhydride. This is what is acetic anhydride, which is made from acetic acid. By heating two acetic acid molecules, this compound is called acetic anhydride. We need a catalyst. We need concentrated sulfuric acid as a catalyst. This is a catalyst. What is going to happen is the hydrogen, phenolic hydrogen, will be replaced by this group, CH3CO group. This is called acetyl group. Hydrogen replaced by acetyl group. That's why the process is called acetylation. Removing acidic hydrogen by acetyl group. This group is acetyl group, CH3CO group. So what we get is nothing but aspirin. This is what is aspirin, made by acetylation of salicylic acid, which is made from phenol by using the name reaction called Kolbe-Schimdt reaction. This is what stands for aspirin. It can also be called as acetyl salicylic acid. Acetyl salicylic acid, since it is made by acetylation of salicylic acid. If you want to give iopectine, its iopectine will be as follows. It will be called as 2-acetoxy. This group is called acetoxy, and the rest of the compound is benzoic acid. What is its use? It is used as an analgesic, pain reliever. It is also used as an antipyretic, means which brings down the body temperature. So aspirin acts as both analgesic as well as antipyretic. Now it is said that we should never take aspirin empty stomach. Because if you take aspirin empty stomach, what is going to happen? Aspirin will go into the stomach. In stomach there will be an acid, and in the presence of acid, aspirin in the stomach will convert back to salicylic acid. It will get hydrolyzed into salicylic acid. And salicylic acid is going to damage the walls of your stomach, causing ulcer. So if you take aspirin empty stomach, it causes ulcer, because in stomach it converts back to salicylic acid, which causes ulcer in your stomach. So aspirin should never be taken empty stomach. So this was the preparation of aspirin from salicylic acid, which was prepared from the reaction that is called kolbe-Schimdt reaction. Now we are going to discuss the third and the last category reaction of the phenol, which we can put in the category called miscellaneous reaction, in which first of all we are going to discuss the reduction of phenol and then the oxidation. It has been found that you can reduce the phenol into benzene. You know what is reduction stands for? Reduction means removal of oxygen. So phenol, if you remove oxygen, you are going to get it reduced to benzene. Let's see how do we remove oxygen from benzene. So you take phenol, heat it strongly with zinc dust, heat it with zinc dust. Zinc is going to take away this oxygen, it will become zinc oxide. And what you're left with is nothing but it gets reduced to benzene. So in a nutshell, from phenol, if you want to remove this group, or if you want to cut the head of phenol, remove OH group, heat it with zinc dust, you will get benzene. Then we are going to talk about aerial oxidation, that is oxidation with the help of the air. You know, air contains an oxidizing agent, oxygen. So if you do phenol, the aerial oxidation, you keep phenols exposed to air for some time, it turns into pink color. Otherwise it is not pink in color. But when you expose it to air, which contains oxygen, it becomes pink. Why does it become pink? Because phenol gets oxidized into a compound called quinone. And this compound quinone is nothing but pink in color. So sometimes they ask you a reasoning question that phenol, when exposed to air, why does it become pink in color? Because of the aerial oxidation, it converts into a pink color compound called quinone. So these are the two other reactions, miscellaneous reaction of phenol, in which we can reduce phenol to benzene. We can just remove this OH group, convert it to reduce into benzene by heating with zinc dust, and by aerial oxidation it converts into a pink color compound called quinone. So these are all about the chemical property of phenol. We discussed three chemical properties of phenol. Number one was acidic nature of phenol. Number two was electrophilic substitution reaction of phenol. And these are the two other reactions, which is nothing but called your reduction and oxidation. This comes under the third heading, miscellaneous reaction. Now we are going to see how you can test the phenol in the lab. What is a chemical test of phenol? In fact, you have got a practical also to do the chemical test of phenol in the lab. When you come to the school, in case the school reopens, we'll do it in the lab also. Chemical test of phenol. And this test which we are going to give is valid only for phenol. When we were discussing the electrophilic substitution reaction of phenol with bromine, if you remember, I told you that phenol, if you put bromine in the presence of water, remember we get a tri-substituted product, 2,4,6-tribromo-phenol, and I told you at that point of time, this is going to be a white PPT. So if in an unknown compound you put bromine water and you get the formation of white PPT, it has to be the simplest member of this group, that is the phenol. Because you get the formation of insoluble white compound, which is 2,4,6-tribromo-phenol. So that can be also taken as a test for phenol. Second test of phenol is the one which we will do in the lab, phenol. If you treat it with a solution of neutral ferric chloride, you take a neutral solution of ferric chloride, immediately you get the formation of a violet color. You get a compound, complex compound, which has a violet color. Now what is the reaction? 6 molecules of phenol is going to form a complex with Fe3+, obviously comes from ferric chloride. You get a violet color compound, a complex compound which is having a violet coloration. This complex compound is formed which has got the violet coloration. It's a violet colored complex compound. If you want to know its name, it is called hexaphenoxyferrate 3. It's called hexaphenoxyferrate 3. So if you want to differentiate chemically phenol from any other compound, you can go for the test, that is neutral FeCl3 test, and you will get a violet color compound. You will not get by any other compound except from phenolic compound. Phenol, already I have told you, the dilute solution of phenol do turn blue litmus red because of its acidic nature. So I show you the question. Suppose they ask you to chemically differentiate between phenol, and let's say you have to differentiate it from a compound called benzoic acid. Benzoic acid has to be differentiated from phenol. Very simple. Phenol, we have just seen, you put neutral FeCl3. We are going to get which coloration? Violet color. In the case of benzoic acid, if you put neutral FeCl3, answer will be no reaction. Because this test is exclusively given by nothing but phenol. You don't know by now what is phenol, in which OH is directly attached to the benzene. So phenols are going to give violet color with neutral FeCl3, and no other compound gives violet color with neutral FeCl3. Now the assignment which I put forward in the group on phenol, there was some conversions, 7-8 conversions which were asked in that particular writer. I'm just doing those conversions for your reference. You can just match your answers if you have done it. Otherwise you can practice it and then complete your answers. The conversions which were given in the notes given below the video link were as follows. The first one I asked was to convert chlorobenzene to phenol. It was just to revise about phenol what we have done. If you do those conversions, all reactions of the phenol will get revised. So you do know chlorobenzene to phenol, it was a Dawes process, nucleophilic substitution reaction. Chlorobenzene react with aqueous NaOH. You have to use a very high temperature, very high pressure. Remember, I told you because the carbon-chlorine bond in chlorobenzene, partial double bond, difficult to break, so will not get substituted. But under drastic condition, it will break. You will get first of all the salt of phenol, sodium phenoxide. It is only when you acidify the medium, you will get phenol. Phenol will be formed in the first step because now all of us know that it is acidic in nature. So as soon as it will form, it will react with unreacted NaOH and convert it into a salt. So this was the first conversion. The second one that was given was nothing but, again for revision purpose, aniline to phenol. This also we have done in the lab preparation of phenol. How do we convert aniline to phenol? It is, first of all, we convert aniline, which is benzene with NH2. We convert it to a diazonium salt. You know what is diazonium salt? How do we make it? By a reaction called diazotization reaction. Sodium nitride HCl around 0 degrees Celsius. We get the formation of the diazonium salt. This we have already discussed. It's just the revision part. We have done in the lab preparation of phenol. Acidify, hydrolyze it in the presence of acid. The compound will decompose to give you nothing but the phenol. So this was the second conversion of converting aniline into phenol. The third one was to convert benzene into phenol. You can use the third method. It was given in the sequence. Benzene into phenol. You do it sulfonation, concentrated sulfuric acid. Sulfonation, you know, electrophilic substitution reaction. You will get benzene, sulfonic acid. Make a salt of benzene sulfonic acid by reacting with NaOH. You will get benzene with SO3Na called sodium benzene sulfonate. Heat it with NaOH strongly. Heating with NaOH solid strongly, the thing is called fusion. Followed by acidification. Otherwise you don't get a phenol, you will get a salt of phenol. You will get the formation of phenol. So these were the three conversions given over there to convert chlorobenzene to phenol, aniline to phenol, and then benzene to phenol. Let's go to the fourth The fourth one was nothing but, it was asked from the cumene process, which I told you was the commercial method to make a phenol. That was the fourth question, to convert phenol into cumene into phenol. You know what is cumene? Cumene stands for isopropyl benzene. So we have got isopropyl benzene. Cumene we want to convert into phenol. Remember cumene process? First of all, we oxidize it. We get an oxidized product. We get cumene hydroperoxide. It was the reaction is already done, cumene process. You get cumene hydroperoxide. When you decompose it but dilute sulfuric acid, you get the formation of a compound called phenol, plus you get acetone also, which is also a very important compound. So that was the fourth question of converting cumene into phenol. Simple revision of the cumene process. You will find all the conversions which are given in the write-up, but actually just to revise phenol reaction what we have done. The fifth question was nothing but converting phenol into 2,4,6 tribromophenol. This we have seen just now. You know, this reaction is taken as a test for phenol. So what we do, we take phenol, subject it to electrophilic substitution reaction with bromine in presence of the polar solvent. Remember, polar solvent, then only we get a tri-substituted product, and we will get the formation of 2,4,6 tribromophenol. Simple electrophilic substitution reaction, halogenation happening in the polar solvent. The next question was phenol into, if you remember, if you see the notes, it was phenol into 1,3,5, this is interesting, 1,3,5 tribromobenzene. 1,3,5 tribromobenzene. So basically what you have to do is that you have to take phenol and you have to convert into this 1,3,5 tribromobenzene. If you compare this structure with the above one, if you see, it is same as that of 2,4,6 tribromophenol minus OH group. If you remove OH group from this compound, you will get this 1,3,5 tribromobenzene. So what you do the first step, bromine, water. We will get the above compound 2,4,6 tribromophenol. And now if you want to make it 1,3,5 tribromobenzene, what you have to do is that remove OH. And I just told you that in phenol, if you want to remove OH group, heat it with zinc dust. If you heat it with zinc dust, what is going to happen? This goes away and you get the benzene. So this is how we can convert phenol into 1,3,5 tribromobenzene. So these were the other three conversions. Number one, cumene into phenol, application of cumene process, just to revise. Fifth one was phenol into 2,4,6 tribromophenol, electrophilic substitution reaction with halogen. Next one was phenol into 1,3,5 tribromobenzene, again extension of this particular reaction. There were 3-4 more conversions, you can have a look at it. The seventh one was phenol into 2,4,6 trinitrophenol. That is also called as nothing but picric acid. Most of us know, very strong acid. 3 electron withdrawing group, 3 nitro group. So this everyone should be knowing. Phenol subjected to a nitrating mixture. You know now by now what is a nitrating mixture? We heat it with concentrated HNO3 and concentrated sulfuric acid. Try substitution. Electrophile NO2 plus attacks at all the ortho and para position, and you get the formation of picric acid. You get the formation of picric acid. And extension of this conversion was the 8th one, and that was phenol into 1,3,5 trinitrobenzene. It is same as that we did that one, phenol into 1,3,5 tribromobenzene. So very simple, now everyone can do this. Do this first step and then heat it with zinc dust, this will go and you will get 1,3,5 tribromobenzene. So in this conversion, this will be the first step. Then second step would be heat with zinc dust. You will get 1,3,5 tribromobenzene. The ninth question was again a revision for Reimer Tiemann reaction. It was asked convert phenol into salicylaldehyde. Direct Reimer Tiemann reaction. We have done just now in today's class only. That was the first reaction we did. You take phenol, dissolve in dilute NaOH. You know, phenol doesn't dissolve readily in water, so we dissolve because of its acidic nature. We are going to put in dilute NaOH. You will get sodium phenoxide. You put chloroform, 340 Kelvin, followed by acidification. You are going to get none other than salicylic. You want to make salicylic, a direct application of Reimer Tiemann reaction. If you see the 10th conversion, 10th one we have told you to convert phenol into benzaldehyde. So it's very simple. If you want to make phenol into benzaldehyde, convert phenol into salicylic. Now if you want to make this into benzaldehyde, you have to remove OH group. Now you know how to remove OH group. Heat it further with zinc dust. This OH will go off, and you will get nothing but benzaldehyde. So if you wanted to convert phenol into benzaldehyde, make it salicylic, heat with zinc dust, this OH will go away, and what you are left is nothing but your benzaldehyde. So these were the few practice questions that was given in that write-up, and these are the answers of those questions. After seeing these solutions, you can try later on without looking at these answers. So today we have finished the whole chapter, that is alcohol phenol ethers, that's over. From tomorrow onwards we start with another chapter of organic chemistry, that is haloalkanes and halogens. I will be putting the assignment also of this chapter on the group. Try to solve it as soon as possible. Thank you. Have a nice day. Take care.